Bismillahirrahmanirrahim. So the second lecture about ID3 algorithm about decision trees. If you recall, in the last lecture we discussed about the decision tree algorithm, and we said that to make the decision tree, the first and the most important thing is to figure out the attribute on which you will have the split root node and then the next set of nodes until you reach the leaf nodes. For that, we discussed the entropy and we said that it is a measurement of how uncertain the data is. So once you measure the entropy on the original data, here I write it as E of S, so E stands for entropy. So the entropy of the original data without using any attribute minus the entropy you get from using that attribute. So for instance, if you recall in the last lecture, we had this problem when we said that the major of a student will determine whether the person likes or does not like the film Gladiator. So to calculate the entropy of major, we first had the three possible values of this attribute. For each value, we calculate the entropy and we multiply the entropy by the probability of this value. So the probability that the major will be math, that is 0.5. If it is math, then there are 4 people, 2 of them will like the film and 2 will not like the film. So 2 out of 2, which is an entropy of 1. For history, the probability is 2 by 8, which is 0.25, and since it is uni-label, only one class in here, we have an entropy of 0. Same goes for CS, we have an entropy of 0. So to combine, we have the probability multiplied by the entropy. You multiply these values and you sum it to get the entropy of the attribute major. So this is the formula in a generic form. S of V is the value. So in our case, it was math and then history and CS. So 3 possible values. We calculated the probability and we multiplied with the probability of with the entropy of that value. In this lecture, we are going to solve an example so that we are able to better understand how to make that decision tree. For this, let us consider this data. In this case, this is data corresponds to 14 days. So you can see from here day 1 through day 14. There are 4 attributes: outlook, temperature, humidity and wind. Whereas this play tennis is the category that we are trying to label. So it's going to be a no or a yes. So there are only 2 classes here. The first 4 are the attributes and the final one is the category. So the first thing is, as we see in the formula, the first thing is we need to calculate the entropy of the data without using any attribute. So we are going to calculate the entropy of this data. The entropy is always calculated based on the categories. So in this case we have 1, 2, 3, 4, 5. So there are 5 no. So no. So 5 no. And there are total 14. So there are 9 yes. So to calculate the probability, we will have 5 by 14 and 9 by 14. These are the 2 probabilities. So E of S, as you may recall, it is minus P naught log of P naught minus P1 log of P1. In this case, this is 9 by 14 log to the base 2 of 9 by 14 minus, there is a minus sign over here. So this again with the minus, and then we have 5 by 14 and log to the base 2 of 5 by 14. So this 9 and 5 correspond to the yes and no of the category, and 14 is the size of the data. So if we solve for this, we end up with 0.94. So this value is the entropy of the data without, so this is this entropy or this entropy. So we have found the entropy without using any attribute. Next, we have to find the entropy when we use the attribute. So we have 4 attributes. Let's try with wind. So let's try what's the entropy if we use wind as an attribute. So here we have, so E of S is 0.94. We just calculated that, minus. So for wind we have, there are 2 kind of values, strong and weak. So let's count how many weak there are. There is 1, then 2, then 3, 4, 5, 6, 7 and 8. So there are 8 instances of weak, which means there are 6 instances of strong. So this is going to be 8 divided by 14. Now 8 divided by 14, this is this part of the value. This is 8 divided by 14. Now we have to calculate the entropy where S wind is equal to V. This is going to be followed by minus, and or we can have a plus here because we have a bracket. So plus, we are going to have 6 by 14 and the entropy of S strong. So wind can be either weak or strong. So we see here there are 1, 2, 3, 4, 5, 6, 7, 8 weak, which means there are 1, 2, 3, 4, 5 and 6 strong. So we need to calculate these values. Now we need to calculate the entropies. We have the probabilities, we need to calculate the entropies. So I use this sum because there is a summation over here. So S of weak, what this means is now we are going to only look at we are not going to look at the entire 14 data, but we are going to look at the 8 values. So these 8 values correspond to where wind is weak, and in those 8 values we are going to count the number of yes and the number of no's. So if we look, if where the wind is weak, we have 1 no and 2 no's. So there are only 2 no's, it means there are 6 yes. So this can be expanded as minus 6 by 8, there's a minus over here, log 2 of 6 by 8 and then minus 2 by 8 log 2 of 2 by 8. So this 6 and 8 correspond to their total 8. 6 of them are yes and 2 are no. So we use this, and this will give us equal to 0.811. Similarly, for this part we have, there are total 6 values. So we have 6 values over here. We have 6 values over here. So if we look at the 6 strong, so this is strong. We have 1 is no, the second no, and the third no. So there are 3 no's and 3 yes. So in this case we have 3 by 6, so minus 3 by 6 log of 3 by 6 and minus 3 by 6 log of 3 by 6. So if you recall, when they were equally divided, the entropy was always 1 maximum. If it is one-sided, the entropy is 0. If it is equally divided, the entropy is 1. So plugging in these values, we can have 0.94 minus, and then here we have 8 by 14 multiplied by 0.811. So we get this value from here, and plus we have 6 by 14 multiplied by 1, because this will evaluate to 1. And this entire thing is going to give us 0.048. So this is the gain that we have. This is the gain that we get due to the attribute wind. So if you use wind as a root node, this is the gain we have. However, as we see that wind is not the only attribute. There is humidity, there is temperature, and there is outlook. So like we computed for wind, we have to compute for humidity. We also have to compute for temperature and outlook. So we'll have 4 values, and then we'll choose the highest value because it's the gain. The one with the lowest amount of entropy is the one that's going to give us the highest amount of gain, because we are subtracting it from 0.94. So if this value is small, this resultant will be high. So the gain should be high. So for wind we have 0.048. Here we have calculated for humidity, for wind, for outlook, and for temperature. So each have their own value. We see from here that outlook has the highest gain. So this means the root node of the tree will be based on outlook. So which we can see over here. So when you look outlook for your root node, there are 3 possibilities in outlook: sunny, overcast, and rain. If you use sunny, there are 2 yes and 3 no's. If you look at outcast, there are all 4 yes and 0 no's, which means that you can terminate this node because they are now pure. There is no confusion. There is no mixture between yes and no. It's only yes here. For here we have 3 yes and 2 no's. So there's confusion over here and there's still confusion over here. However, we're done with this one. So for this now, we have already used outlook. So there are 3 attributes that are remaining. So we are going to use one of the 3 attributes here, and we have to repeat what we just did. So we are going to find the information, the gain, because of the other attributes. So, but in this case, we are only going to limit ourselves to those part of the data where the outlook is sunny. So there are in total 5 elements. So day 1, day 2, day 8, day 9, and day 11. There are 5 days in which the outlook is sunny, in which 2 days they play tennis and in 3 days they don't play tennis. So out of these 5 values, we are going to calculate the gain for humidity, the gain for temperature, and the gain for wind in a very similar fashion that we did in the previous slide. So the resulting values are 0.97, 0.57, and 0.019. So we see here again that humidity has the highest gain, which means that the next attribute here to be used is humidity. So the entire tree will be something like this. So outlook, if you look at overcast, then it is yes. If it is sunny, you need to further consider humidity. For humidity, if the humidity is high, it is no. If it is normal, it is yes. And if it's rainy, then you have to look for wind, and you go like that. So in the tree, at the leaf node, it is either a yes or a no. So here is a no, here is a yes, here is a yes, here is a no, and here is a no. And in the root node and the intermediate node, it is a value, it's an attribute. This is an attribute, this is an attribute, and this is also an attribute. While as in the leaf node, it is one of the 2 categories. So this was the ID3 algorithm, which uses entropy as the basis for splitting. However, entropy is not the only possible way in which you can split a node. Remember, we chose outlook because it has the highest gain in terms of entropy. So other methods have some other possible metrics. For instance, the C4.5, instead of using entropy, it uses a gain ratio, which is gain of A divided by the split information, and that's how you compute that. So this is another possibility in the C4.5 algorithm. Instead of using entropy, you use a gain ratio. Similarly, another possibility is using the Gini. So Gini is a probabilistic value, the probability of the value multiplied by the conditional probabilities. So we'll explore this slightly in the next slide. So suppose we have this data. So there are either triangles or there are squares, and there are three colors: red, yellow, and green. And there's a mixture of which color and which shape you have. So if you want to predict the shape, so the shape is either a square or a triangle. So just like in the previous case, we first calculated the entropy using the raw data without using any attribute. So here also we are going to calculate the Gini using the raw data and without using any attribute. So for that, the number of squares, so how many squares do we have? 1, 2, 3, 4, 5, 6, 7, 8, and 9. There are 9 squares, which means the probability of square is 9 divided by 14. And 1, 2, 3, 4, 5. So there are 5 triangles, and the probability of a triangle is 5 by 14. So using this, we have 9 by 14 multiplied by 5 by 14. This is the Gini, this 0.23 is the Gini index or the Gini value corresponding to the data without using any attribute. Next, we see that what if we use an attribute? Can we reduce the Gini or not? So if we use color as an attribute, if we look at red, there are 1, 2, 3, 4, 5. So there are 5 red shapes there. Among those 5 red shapes, we have 3 squares and 2 triangles. So probability of red is 5 by 14. Similarly, probability of green is 5 by 14 and probability of yellow is 4 by 14 because there are only 4 yellow shapes. Next, we multiply it by the Gini. So if we now look at this subpart of the data, this subset of the data, here we have 3 squares and 2 triangles. So the Gini here is 3 by 5 multiplied by 2 by 5. Notice that now we are not using 14 because we are concerned with only this subset of the data. This subset where the color is red, there are only 5 elements here. So 3 by 5 and 2 by 5, 3 squares and 2 triangles. So you multiply this Gini and multiply it by the probability. So if you look at it, so this here corresponds to the value for red. Next we have the value for green. So this is the probability of green. This is the number of squares in green and this is the number of triangles in green. So this corresponds to green and this corresponds to yellow. So here you see that it's interesting to note here that all 1, 2, 3, 4 all are squares. There is no triangle. So whenever an entropy, or if the same with Gini as well, when you have all values belong to only one class, the answer is 0. So this multiplied by, because we have 0 over here, this entire thing will become 0. So again, as with the entropy, we have a summation over here which causes these sums. So this red plus green plus yellow. Since yellow is 0, we have red plus green. So this is going to give us a value of 0.171. So instead of using instead of using entropy, we could have as well used Gini, or we could have used the gain ratio. So different metrics, different versions of the same algorithm. The framework is the same. So this is the Gini because of color. Originally, if we did not use any attribute, we had 0.23. If we use color, then we have 0.171. To subtract it, we get the gain. So this is the gain that we get using color as an attribute. If there were more attributes, we could have calculated for other attributes and then decide how to make the decision tree. Next, we see that decision trees are extremely popular category of machine learning algorithms. They are used in a variety of disciplines. For instance, in credit risk assessment, in medical diagnosis, in market analysis, in bioinformatics, chemistry, and recent survey has shown that there are, if you look at PubMed, it's an archive or it's a library of journals, research journals. You'll see that there are 6,906 papers that are related to decision trees. So that means that it is quite popular. Now we move on to the computational complexity of making a decision tree. So you may recall from your data structure course that what trees are and what's the computational complexity of making a tree. So the computational complexity here is n into m square. N is the number of examples. So in our case for the play tennis, it was 14 examples, so there were 14 days. So we have n in our case here was 14, and then there was 4 features. So there were 4 features over here. So nm square, this is the complexity that is needed to create that tree, and this is for the training data. For the test, it is usually very fast, just like we had for neural networks or for deep learning. The training takes a time, the test is very fast, it is linear. In this case, since it's a tree, it can be even less than a linear, it can be a log value, so sublinear. Another important thing we need to understand is that of overfitting and underfitting. And this is not just specific to decision trees. This happens in all other machine learning algorithms as well. So overfitting is the case where you tune your algorithm very specifically to the amount of training data you have, so much that you develop some rules that may be true for the training data, but they are not true in general. For instance, if I were to say that there are 20 students in front of me, let's say 10 of those students were GKN students, and by chance those 10 people were wearing a blue shirt on that particular day. So there are 20 students, 10 of them are GKNs, and because maybe there was some function or something, all 10 of them were wearing, or maybe 8 of them were wearing a blue shirt. So in that case, if I say that everybody who is wearing a blue shirt is a GKN, this may fit my training data, but this is not true in general, because that happened on that specific day. On any other given day, they may be wearing a shirt of another color. So we say that a data overfits when you tune it too much to the training data, such that it may or may not be true for the test data. So as we can see in this graph, the accuracy increases as you are learning. Both the training and test increases. At a certain point, the training data continues to increase because now you are trying to fit your model to the training data. However, you are now learning, you are now overfitting it, and the test data may not perform as good as the training data. So you can see that the test data increases, and after a certain plateau, it will start decreasing, which means that all this portion, this entire portion over here, this is overfitting. Ideally, we should have stopped somewhere over here. So the way to prevent this overfitting is in trees, you may recall from data structure, is pruning. Now there are two ways of pruning a tree. The first one is pre-pruning and second one is post-pruning. So for that, consider an example where we have an attribute, let's say attribute A1, and you split on this attribute and you make a tree. And then here we use A2 and you split on A2. So after this, assuming you have 9 positive values and maybe 1 negative value, and here you have 4 positive values and 0 negative values. In this case, in the other case, if you split it over A3, then assuming you have 100 positive values and just one negative value, and here we have 5 positive values and 0 negative values. So you see that in this case, if I had decided to stop over here, suppose I don't split on A3, how many elements do we have? How many instances do we have? 100, 101 and 106. So there are total 106 elements. Of those 106, we will have 105 positive and 1 negative. So because of this 1 negative, I decided to split this tree and go one level down. But I still have this problem. Maybe I decide to go another level using A4 or something like that until I can come up with this. Maybe we have 101 or something like that positive here and 1 negative over here. So I could continue doing this, or I can decide that I will stop at A3. Now I do realize I have one negative value, but I am willing to tolerate this value because this will make the tree a lot shorter. It means that I am less likely to overfit on the data, because the overwhelming majority here is positive and there is just one instance. I'm going to assume this one instance here is just an outlier instead of the norm. So this just happened to be here, it's an outlier, and hopefully it won't be here in the test data. So if I stop here, this is it. I don't need to go any further. So the difference between pre-pruning and post-pruning. In pre-pruning, when I have 105 positive and 1 negative, I will say, okay, that's it. I'm not going to go any further. I'm not even going to make this. So that is pre-pruning. In post-pruning, I am going to make this tree. And once I have made this tree, I say, okay, I went 2 levels deep. So I have 2 levels and I just gained one simple example. So I don't need this. I did build the tree in the first place, but afterwards I'm going to say this is going to be pruned. So in pre-pruning, you don't build it, you stop right here. In post-pruning, you first build it, then later realize that the gain you are getting is not that much and you decide to prune it. So that's the difference between pre-pruning and post-pruning. So pre-pruning is faster because you don't build it in the first place. So that's the preferred approach. And a good rule of thumb of how do you know when to prune or when not to prune, that will depend on the task you are performing. So if you are using maybe a video and you're trying to find the emotion of people, which may be helpful but they are not critical, and you say, okay, in this case I have a 95-98% accuracy, that's fine, I don't need to go any further. On the other hand, if you are using maybe signature recognition, in that case a 95% accuracy is not good enough. You probably need to go to 99.9 or 100%. So in that case you are going to go for the full tree, even if it requires you going newer levels. So it really depends on the amount of tolerance that is acceptable in the domain in which you are working. So once a tree is made, the final thing that we need to do is generate rules from those trees. So if I have a tree here, x1 is the age of a person, x2 is the years in their job, x3 is the gender, and x4 is the job type. So if I look at this tree, suppose I have built this tree, now what I do is I make a rule out of it. So first, if age is greater than 38.5, yes, and x2. If your experience is greater than 2.5, so if age is greater than 38.5 and experience is greater than 2.5, then the output y is 0.8. So for each leaf you have, because there are different values in each leaf, so for each leaf we are going to have a rule. So 1, 2, 3, 4, 5 values, you end up with 5 rules. However, if it was the case in, for instance, we had, let's look at, so here, in this case, there are 4, 1, 2, 3, 4. But are we going to have 4 rules? No. because this is yes and this is yes. I can combine these two. I can say if outlook is sunny and humidity is normal, or if outlook is rainy and wind is weak, then yes. So I can combine these values. So there are going to be only two values. The two no's will be combined and the two yeses will be combined. However, in this case, since it was not a category but a real value and they are all distinct, there are 5 of them and we have 5 rules. So you can see from here that this is very easy to understand. Even for a layman, it's very easy to understand. So suppose you are the technical person, however the decision is being made by the business manager or the CEO, it's fairly easy for the CEO to understand this language. Instead of telling him that this is the neurons and this is the layer and this is the deep learning part and this is the convolution, they have no idea what you're talking about. But in this case, it is fairly easy to understand. And this is one of the reasons that we say that it is simple to understand and interpret, which is a reason for its popularity. It's very simple to use even by people who are not technical. So it is going to have a value even with little hard data. So even if you have a hard data, if you have a small amount of data, you are still going to be able to come up with a decision tree. And it's a white box. White box means the interpretation of the intermediary steps are also intuitive. So for this, what I have is people whose age are greater than 35. They are the people whose age are greater than 35. If I were using deep neural network, what's the meaning of the output after the second convolution layer? I don't know. I know the input and I know the output. What's the interpretation of the output of the second convolution layer? It's not very straightforward. It's not easy to interpret. So decision tree is a white box because you can interpret it, but a neural network, the hidden layers of neural network or the hidden layers of a CNN are considered as a black box because you have the input, you have the output, you don't really understand or interpret what's going on in between. And finally, it can be used with other decision techniques as well. So this was an example of a single decision tree. I could have made multiple decision trees and then combine them together. That's called random forest or bagging and boosting approaches, which is not a part of this topic, but maybe if there is time in this course, maybe toward the end, we are going to look at one or two examples of bagging, boosting or random forest, because they are very powerful techniques in doing this prediction and categorization. So I hope by looking at this example, you are better able to understand how the decision tree works. And you can practice with this. For instance, in our example here, we calculated using wind. So maybe what you can do is calculate using outlook and using humidity and temperature. So we have the answer, so you can verify that you are getting the right answer or not. So do practice it, because maybe in next week or the week after that, we are going to have either a quiz or an assignment based on this ID3 algorithm. So thank you for listening to this lecture. And if there are any questions at the end of the week, we are going to have the question answer session. You can point out something you don't understand. You can point to the slide number. You can send me an email, or I'll try to answer it as best as I can. So thank you very much.